Is that me? Okay, hello everyone. Hello, it works? Okay, great. I'm Ben, and I'm going to talk about a spectrum of type soundness and performance. So to begin, I have two old questions on the slide. One asks if there's any interesting properties that might lie between full type soundness and unsoundness. And the second question asks, what's the relationship between type soundness and performance? Now, I say these are old questions because in the context of a statically typed language, we've had answers to these for decades. But I claim that in a gradually typed language, or any language that mixes typed and untyped code, these questions are now extremely interesting. Okay, so migratory typing. What I'm interested in is migratory typing, which is the idea of starting with an existing dynamically typed language, designing an idiomatic type system to reason about the programs written in that language, and then ending up at two languages side by side. So on the left, we have a typed language where every program is statically typed. And on the right, we have the existing untyped language. And there's an arrow between these two because I expect that they can interact and share values back and forth. So two compatible languages. To give one example, if we have a typed context that expects a function on natural numbers, we should be able to bring an untyped lambda across the boundary and use it within the typed code. So that is migratory typing, and it's in the same research area as gradual typing, optional typing, concrete typing, and many others. We're fortunate in this research landscape that besides theoretical ideas, we also have a whole space of practical implementations. So the swimming pool here represents the system space of gradually typed languages. I'm going to say from now on mixed typed languages. So here are a few of the names in this space, and you can see there's lots of names. That's right, they all build on similar motivations, but if you look closely at these systems, they're very different from one another. As a case in point, many of them claim to be type sound for some value of sound. If you look closer, they prove very different theorems, and some of them are in fact unsound for mixed typed programs, and their soundness claim only holds for the statically typed portion of the language. So there's some differences here that aren't captured in the literature. Similarly, for performance, everyone wants to be fast, or at least not dead, for some value as fast. But it's unclear what this means as we go between languages. So the state of the art in comparing different approaches to mixed type programming is to make claims that go across languages. Say, language A seems to be faster than language B on benchmarks that we ported from language A to language B. So in this paper, we break from tradition, and we've gone about comparing different approaches to mixed type programming in a systematic way. So in particular, we start with one model of mixed type language, and then based on what we've seen in the literature, we've extracted three semantics for programs written in this mixed language. Their names are higher order, first order, and erasure, and these names communicate the most important part, which is what the semantics do at the boundary between typed and untyped code. With this model, we now have apples-to-apples theory, so we can directly compare the meta theory of the three semantics. Then we went further and used the models to build implementations for racket and typed racket as the surface language. So on the left, we have three models, and on the right, we have three compilers. So now we can compare the results of running the same typed racket program against three semantics. And now we have apples-to-apples performance numbers that I'll tell you about today. So let's get started with the model. What we have is as simple as possible for the things that we want to express. So in particular, here first, we have grammar of types. And what you should take here is we have a co-inductive type for functions, an inductive type for pairs, and we have two base types, one for integers and one for natural numbers. These base types are in a subtype relationship, which reflects how a programmer using a typed language can use the type system to make a logical distinction that may or may not be supported by the underlying machine that they're running their programs on. Then we have an analogous grammar of values, where we have a higher order value for functions, a simple data structure, and two base values. And these base values are in a subset relation, and this reflects how a programmer in a dynamically typed language will use predicates to identify a subset of the value domain and then write programs based on that subset. We have a simple language of expressions. The important part for today is these two boundary terms, dyne and stat, which let you go between dynamically typed code and statically typed code to form a well-typed program. So here's how those two rules interact with the typing judgments. Dyne starts in typed code and goes up to untyped code, and stat starts at untyped code and goes up to typed. You'll notice there's no unknown type, and there's no type consistency relation in this model. So those raise very important questions for the static type checker for the language. But what we're interested here is what is the semantics of running a program that mixes typed and untyped code. Right, so using the model, we can write some programs that we care about. So in a type environment, where fib is a function that expects a natural number, norm is a function that expects a pair of naturals, and map is a function that expects a function on natural numbers, we can write programs that apply these typed functions to untyped values. So, or in a nicer presentation, we can have typed contexts on the left and untyped values on the right that are trying to cross a boundary from untyped code into typed. And then the types above the arrows indicate the types that the typed context is expecting. So in our study of the literature, we found three main approaches to defining semantics for these languages. We'll start with H for higher order. So the goal of the higher order semantics is to fully enforce types at the boundary between typed and untyped code. So in terms of our examples, if typed code expects a natural number and receives an integer, it's rejected. The semantics raises an exception. Similarly, if typed code expects a pair of naturals and receives a pair where the elements are not naturals, it's also an error. And now, if typed code expects a function and receives a lambda, it conditionally accepts the function. That's what that orange disk is indicating. If you're familiar with higher order contracts, that's exactly what's happening here. That's what the orange disk means. If you're not familiar, we'll step through an example. So the function comes across, and it's represented as a disk in the typed context. And now, as our typed side computes, and eventually gets to a position where it applies the disk to an argument, we cross back into untyped code. So now that natural number 1 goes from typed to untyped. The untyped code now computes its result, and when it's finished, it passes it back along another boundary, back into typed code. And here the value that comes back is checked against the codomain type of the function, which we have because we carried it around in our disk. So here the higher order approach can say, I've detected a type error, and it's due to that boundary up at the top, where that untyped function came in and I said, you're conditionally okay. So that's the higher order approach, and I know of 4 systems in the literature that implement this approach. Next, let's do 1 for first order. The goal of the first order approach is to avoid these proxies, or these disks that we had before, and to check only type constructors at the boundary between typed and untyped code. So if we're expecting a natural number and receive a negative number, the negative number is rejected because it doesn't match the outermost shape of typed natural number. But if we're expecting a pair or expecting a function and receive, respectively, a pair or a function, those are both allowed to cross over into the typed context because they pass the first order check. What happens next? So let's take our norm example. And I said that the pair passes the nat star nat check, so that pair crosses over from untyped code into typed. I've colored the components of the pair differently to indicate that they are untyped values. We know, looking at the slide, that it's -1 and -2. But in principle, these untyped values could be anything because they haven't gone through any sort of check, any sort of type check. So as our typed side computes, and we eventually apply a selector to the pair, what happens next is subtle, and it depends on what the expected type of the selection operation is. So we're in typed code. This call to second has a static type, and we use that type to say what check needs to happen at this boundary between an untyped blob and the typed context. So if the boundary expects a natural number, then the component of the pair will be rejected at the selector. But it could also expect an integer, because int and nat are subtypes in a subtype relation. And if the type code expects an integer from the selector, then that untyped value is allowed to cross into typed code. And what we have is a silent failure, where a value that was a natural number up at the top has now been accepted as an integer. Oh, so this is what happens in first order. What I've described is, the approach I've described was pioneered in reticulated Python. And I know of two other systems that are following a similar approach, Pauline and Grace. Next up, E for erasure. The erasure approach ignores all types when you run the program. So no matter what value tries to cross in from untyped, the types don't add any restrictions, and the value is free to go. What does this mean? It means we can apply a typed function to a value that lies outside its domain. This might give us an error. This might lead to the function diverging. It might give us a sensible result. Really, anything could happen. We have another silent failure of the types. The erasure approach is very popular. It's very easy to implement, and it gets you static type checking and IDE tools. And you don't have to worry about implementing a new semantics because you can reuse the one that you already have for your dynamically typed language. Okay, now we've seen three approaches to running the same example program, and we've seen these approaches lead to different results. There are many more examples in the paper, especially showing how these different results can affect a programmer's work and what they need to do to debug a program. But let's talk more generally. We all know the point of sound static types is to prevent certain runtime behaviors from occurring. We want to prevent violations of the types when we run the program. So if we imagine a spectrum from catching all violations of the types at runtime, or catching all violations of the types, or catching no violations, we can position these three semantics that we've talked about in subset relations. So we show in the paper, every time that the first order approach reduces to an error, the higher order approach will reduce to a similar error. It'll also catch the violation. And similarly for erasure, anytime erasure detects some violation, first order will also detect the violation. For the counterexamples that show that these are strict subsets, we could see the previous slide. And so this is 3 points on a spectrum. In the process of doing this, we identified two other approaches to checking types at the boundaries. And we conjectured they fit here between higher order and first order. So we certainly have the strict subset relation, and you can see this in the appendix. Yeah, let's move on. There's at least 5 approaches. So we've talked about errors, and we've talked about examples. Now let's talk about soundness. Here's a simplified statement of type soundness for a statically typed language. If I have a well-typed program, there are 3 things that can happen when I evaluate this program. It could step to a value of the expected type that we had at the top. It could diverge, or the program could end in an error. What's the soundness that the higher order semantics satisfies? Well, it's very similar to the soundness that we have for a statically typed language. So in particular, if a well-typed program reduces to a value under the higher order semantics, we know that value has the same type that we expected at the top. For the first order approach, we get a different theorem. If a well-typed program reduces to a value, all we're guaranteed is that the value has the same topmost type constructor as our initial static type. And for the erasure approach, we have an even weaker guarantee. If an expression reduces to a value, we know it's a well-formed value. So this erasure soundness is really telling you evaluation does not get stuck. But then beyond that, nothing else. The types give you no predictive power for how the program is going to compute. So, is type soundness all or nothing? No, absolutely not in a mixed type setting. Now moving on to performance, how does type soundness affect? So like I said at the beginning, we took our models and we used them to define 3 implementations for the type bracket language. This gives us 3 compilers. The first one, H, is what type bracket implemented before our work. So it helps to understand its compilation pipeline to explain how we implemented the others. Type bracket takes a program, expands all the macros in the program, type checks the expansion, then enforces types with higher order contracts, and finally applies a type-directed optimization path. So given that type bracket has a soundness guarantee, it knows that it's safe to apply optimizations using the types as assumptions. For the first order and erasure approaches, we reuse the expander and type checker, but we change the type enforcement. So under first order, we enforce only type constructors in the way I outlined before. And in the erasure approach, we simply throw away the types, and they have no impact on how the program runs. Neither of these include an optimizer. You might ask, why doesn't the first order approach have an optimizer? Because you can at least trust the topmost type constructor in optimization. And the answer is we wanted to compare how these approaches fare in an apples-to-apples setting, exactly as they're described in the literature. So I think optimization is important future work, but for now, let me tell you what the picture is as of today. The method we use to evaluate is the one suggested in POPL 2016, and that is to look at a set of fully typed programs and consider all ways that a programmer could mix typed and untyped code within these programs. So for a program with 10 modules, we wind up with 1,024 ways of mixing types. For more information about the benchmarks, please see that URL. Now, there's lots of data in the paper, but the one result I want to tell you about today is what happens as you increase the number of type annotations in a program. How slow does the program get? So along the x-axis going right, we're adding more types, and along the y-axis, programs are getting slower. And, yep. Okay, the next slide is going to have a lot of data. The red dots represent configurations running the higher order semantics. The blue dots represent the first order, and the green line is erasure. So in cases where you can see the green line, that's the baseline. That's the performance you would get with no types whatsoever. You can see from these that in the middle of the plots, where we have a mix of typed and untyped code, the higher order approach sometimes hits a performance wall, runs extremely slowly. But towards the right, when the program is fully typed or nearly fully typed, the higher order performance improves significantly because its performance overhead only comes from boundaries. And as you eliminate those boundaries or eliminate the critical boundaries, there's no more overhead. And in addition, the benefit of these type-directed optimizations can kick in to make the red dots faster than the green line. In the blue dots for first order, we see a phenomenon where the performance is basically a linear function of the number of type annotations in the program. So here's a sketch of the conclusions that we draw from this data with the wall in the red and the linear increase in first order. And so we can offer some general guidelines. If you're programming in a language that implements the higher order semantics, add types until you've removed all critical boundaries. So then you get the most benefit for your optimizations and the least cost from interactions. If you're working in a first order approach, be careful how you add types. Really, add them only where correctness is essential, because otherwise adding more type annotations is going to slow down your program. And for erasure, add types wherever you like, because it really doesn't matter. Takeaways. So if you're a theorist, I'd like you to take away that type soundness is not an all or nothing proposition. There are interesting theorems that we've shown that lie between full soundness and unsoundness, and they're really about what part of the static types does the reduction relation preserve. We've identified, 3 approaches that lie between full soundness and unsoundness, and I suspect that there's many more. If you're a language implementer, I hope you look at this picture of the landscape and ask whether we can change it or not. So one thing that I pointed out before was the missing optimizations in the first order approach. It's an open question to see whether they would bring the blue line to go below erasure, or whether it's just that it'll still be a linear function, but just less extreme. So yes, can this landscape change drastically, or is it just going to be the same picture with a smaller y-axis? It's a question. And finally, if you're a language user, take note that there are at least 3 ways of running a gradual program, and these ways are going to affect how fast your programs run and how long it's going to take you to debug a program if you have some violation of the types. Before I close, I want to say thank you to a few people who influenced me and or Matthias as we were writing the paper, and that's the end.
Thank you. So there's a question. Can you elaborate on the 2 other approaches you've identified in your intuition about them?
Okay, so the one with C is a lazy version of the higher order approach. So we saw when a pair hit the boundary in higher order, it would check both components of the pair. The C says, just check that it's a pair and add a wrapper that tracks the obligation that the components of the pair need to match the type. The F stands for forgetful, which is based on Michael Greenberg's forgetful semantics for higher order contracts, for space-efficient contracts. The difference between forgetful and this lazy C is that when a value crosses boundaries more than once, forgetful will remember only the most recent. So it's much closer to what first order does, basing its checks on local type annotations.
A related question is, where does this the approach of concrete typing fit?
Let's see. I'm going to answer a different question. We saw all these names at the start, and some of these names are in black boxes. And the names in black boxes didn't appear on the final slide where I had H, 1, and E. Here's the full picture with all the names positioned. The ones in black boxes follow the concrete types approach. The concrete types approach is different from gradual or migratory typing as it was originally proposed because it says every value must come with a type annotation. There's no such thing as an untyped value. So it's an interesting question if programmers will find concrete practical or not. But since it doesn't fit into, my favorite scheme of migratory typing, we have a black box to distinguish. So concrete means no untyped values.
Thank you. So can the 3 instances of soundness that you've identified be recast as 3 different semantics for the same syntax of types?
Come see me after.
All right, we have another question here. Does including runtime type validation in a language that uses erasure changes any of its properties or how it's classified?
Sure. It depends on what the validation strategy you choose is, but I would argue that it's not erasure anymore if you have runtime tag validation.
Okay. So we know that the higher order semantics can, in theory, impact the time complexity of a program. Have you experimented with changing the input sizes for your benchmark to discover whether there are impacts on time complexity?
Oh, yes, there certainly are. This red wall wouldn't be there if there wasn't some exponential overhead. You can't even see the green line in some of these. I haven't included the scale on the y-axis, but some of these are 4-digit numbers.
Okay, so we still have some time. So in what way do the types in the erasure systems actually help programmers?
Sure. The types help because you have a static type checker in erasure. So anytime you've written a program and you run the checker and it detects an error, you've benefited from the types that you've written down. They also serve as documentation for other programmers, and they can also work to help IDE tools to give you autocomplete or other refactorings.
Okay, and maybe a last one. Do you have any ideas for optimization of the first order semantics?
Yes.
He didn't give away, okay. Okay, thank you, Ben, again.